First, look at the difference between them. Why do they look different? Why the one in the middle, steel with higher carbon content, has a kind of flat fracture surface? Okay, so the fracture surface can tell you a lot of stories. Actually, there's this whole new study about teach people how to just look at the fracture surface to determine what is going on before fracture. Let's go back to the notes. Okay, what story it tells us? If you have a super soft material, can you imagine how that fracture surface looks like? If you have a super soft materials, such as gold. If you have pure gold, then it should be very soft. Imagine if you have a gold bar, you pull that bar, how the surface looks like, fracture surface. I'm going to draw a schematic here. If you have an extremely soft material, the fracture surface is going to become a point. So that material will experience a large deformation, plastic deformation, before it fractures. So it will stretch to very, very thin until it breaks at one point. Remember the video we watched last week? When you pull gold atoms apart, you see the layers of the atoms are changing, right? The atoms are rearranging themselves. But with our naked eyes, this is how we say. Everything just shrink down to a point. So we have 100% reduction in the cross-sectional area. So this is extremely soft material under fracture. But for most of the metals, such as aluminum and copper, the surface is going to look like something like this. It's going to have some rough surface, but you will see necking, which means shrink in diameters. So in the fracture surface, you will see cups and corns fracture. This is ductile materials. So for ductile material, you're going to see that rough surface. What happens to very brittle material? If you have a super brittle material, remember the picture showed the middle one, the steel with high carbon content, you're going to just end up with a very flat fracture surface. Okay, that's the difference between different materials. When you look at the surface, fracture surface, you're gonna see different shapes. Next, I would like to show you a video. Wait a second. Sum up.
They're all around us. If we knew more about the way metals broke, then the structures of the future could be safer, more efficient, and even less expensive. Hi, I'm Jeffrey Bomarito, and I devote my time to finding out how and when metals fail. Did you know that every block of metal has tons of microscopic voids inside it? And that these microscopic voids actually play a crucial role in failure. When a metal is stretched or loaded, these voids start to grow and link together until the metal fails. If we look at a copper bar being pulled in tension, we see that it behaves the same. In the center region, it necks down until eventually it fails. Now you might ask, what about those voids? How do we know they're the reason for failure? Well, one way we know is by looking closely at the fractured surface. The surface has many dimples, which is a sign that voids have grown and linked together. Now if we zoomed in on a chunk of metal, it might look like this. If I zoomed in the same amount on a human hair, it would look like this. But if I wanted to analyze this chunk of metal, it would be quite difficult because there are many voids and they're all scattered randomly. In my work, I look at one void at a time, and using a computational model, I look at how it responds to many different loads. I am then able to stitch together the responses of individual voids to understand how the metal will behave on a much larger scale. The simulation you see here is another tension test, where this notched bar is pulled until it fails. One of the very useful things about computational simulations is that we are able to look inside the material to see how the failure process occurs. You can see here that failure occurs as a crack that starts at the center of the member and propagates outward. So, by using a bunch of models of microscopic voids, I'm able to make predictions about how and when larger elements will fail. The truly amazing thing is that these predictions actually correspond to experiments. I'm able to show that damage starts to occur in the center of this element and leads to a crack, which is the same as seen in experiments. The use of computational models such as mine, when combined with simple experiments, will help improve our ability to predict cracks and ultimately help to avoid the failure of our structures. So, as we move into the future, our use
Okay. Now I'm good. If we have a metal bar, the cross-sectional area of that bar is A. We have a force F pulling this bar at both ends. What is the stress inside of this metal bar? Anybody know what's the stress? It's going to be just F divided by A, right? That's not statics. Sorry, but we learned this in this class. So this is a review of chapter 7. Okay, my bad. Okay, this is stress. Let's combine. This is chapter 6, the mechanical property of materials. My bad. All right, we can combine this with stress string diagram. Stress string diagram. Okay. So we can compare that stress we calculated with our stress string curve to see where we are at, right? If that stress is less than the yielding stress, no, that's a tensile stress, sorry. That's tensile stress, the ultimate tensile stress. Yielding stress is probably somewhere around here. If the stress sigma we calculated, it's smaller than sigma y, we know we're pretty safe. Everything is just elastic deformation. And if that stress is below tensile stress, we know this material won't break. We're pretty safe. But what if we add cracks and flaws into this metal bar? Would the stress, would this still hold? So the calculation we're doing here is based on we have a perfectly manufactured metal bar that performs this stress strain curve as we want. But in reality, we have cracks. Let's look at the view of this metal bar. Let's cut it from the middle. If we have any small cracks, let's see, we have a cracks on the surface. Then the length of this crack, it's A. And we have a radius. This crack have a radius rho. The radius means if we zoom into this crack, we're looking at what is that radius. You can think about that as a circle. Radius rho t of the crack. So if we have just one crack in that material, it would totally change the stress, the maximum stress we have. So if you have stress in your material, and we have a new equation here to calculate what is the maximum stress. Maximum stress sigma m equals 2 times sigma naught times A divided by rho t square root. Let me explain what are the, so sigma naught here is applied stress. A here, it's a length of surface crack. All that length could be half the length of the internal crack. We can talk about that later. Rho t, it's the radius of curvature of that crack tip. Oops, curvature. Okay. So now I want you to look at that equation we have. And what is a relation? It's who's going to be larger? Sigma m going to be large, or sigma naught going to be larger? What's the relationship between them? So this sigma naught here, it can be calculated by just what we did here, by using force divided by the cross-sectional area. Or we can just add this guy here, sigma naught. But the sigma m it's where the maximum concentration gonna be around that crack. So if our sigma naught, for example, on our stress strain curve, our sigma is not very large. Sigma naught is over there. It's way below yielding stress. But if we have a crack, that sigma m can be significant, can be somewhere over there based on calculation. So that tells you, even you think you use F divided by cross-sectional area, you get a relatively safe stress. But you should always consider the flaws inside of the material. Because after you go through this calculation of Qm, you're gonna end up with a much larger stress. Oops. So here, keep in mind, if there's cracks, there are cracks. Sigma m gonna be larger than sigma naught. Another question is, what if there's no crack? What's the relationship between Qm and Q naught? If there's crack, Qm, the actual stress inside of the material is going to be way larger than the stress you calculated based on area and force. But what if there's no stress? Oh, sorry. But what if there's no cracks? What's the relationship between sigma m and sigma naught? It's going to be equal, right? If there's no cracks. But in most of the cases, all brittle material, very important, all brittle material contains a large amount of cracks. Almost all brittle materials contains a population of small cracks and flaws. That tells you if you have brittle material in your design, you should consider to use this equation to calculate what is a maximum stress. All right, is that clear? Does that make sense? Okay. And last time we also watched the video. If you have a crack, the crack can propagate, and that speed is super fast. But so here, if we have this crack presents in this material, when would that crack propagate? Another equation that tells us when that crack would propagate. It's called the stress here, it's called critical stress. Critical stress equals 2 times E gamma S divided by pi A square root. So E here, it's a modulus of elasticity. Sigma S, it's a specific surface energy. And A, it's a crack length. The same A as in the previous example, the previous equation. So it's full length for surface crack. And it is half the length if you have internal crack. So that's a critical stress. If the maximum stress in the material is greater than critical stress, we're gonna see crack propagation. The crack propagation will lead to fracture. That's failure. But if the maximum stress is smaller than this, and it's safe. All right, next time we're gonna do some examples to practice how to use those two equations. But that's all for today. Hopefully they will fix this projector next time. By the way, no class on Wednesday. Right? Wednesday is our holiday, right? Trans holiday, traditional holiday. I'm kidding. Yeah, but I will see you guys on Friday.